Hello, so this is me redoing the talk that I gave at CP2023 about the paper Proof Logging for Smart Extensional Constraints. It was joint work with myself and my supervisor, Ciaran McCreesh. So constraint programming solvers sometimes make mistakes, whether that's because of a hardware issue, a software bug, or a flawed algorithm. Very occasionally, even the best solvers will sometimes claim unsatisfiability on a problem that is satisfiable, or claim optimality when there's a better solution out there, or just give a solution that doesn't satisfy the constraints. Now, nobody at CP needed any convincing that this is something we might like to avoid, and that there are certain critical applications where wrong answers are simply unacceptable. So what do? Well, we test our solvers very carefully for starters, but this is tricky for such complex bits of software and is never going to catch absolutely everything. We might also hope for formal verification, but again, the complexity of modern solvers means that even the best state-of-the-art formal verification techniques are quite far from being able to certify all the reasoning that we can do in CP. So what else do we have? Well, as I spoiled in the title slide, this talk is going to be about proof logging. So the idea here is that a solver alongside a solution produces a mathematical proof that can then be externally verified by a verifier program. So this proof is generated line by line during the solver's execution, and the hope is that the verifier is a simple enough piece of software that we can either trust it in and of itself or else potentially formally verify it in and of itself. So this gives us a few things. First of all, if there is a bug in your solver that leads to a wrong answer, the proof isn't going to pass because it's mathematically impossible to have a correct proof of an incorrect result. And when it fails, might even help tell where the bug in the solver actually is. Secondly, and potentially more importantly, when your solver is correct, that then gives you a proof, a certificate for all time that says that this really is the answer to this particular problem. And that even if there was some discrepancy or some reason to not trust your solver, that doesn't undermine the integrity of that particular answer because it has a valid proof. Finally, the proof in and of itself is a useful resource to mine for information. So proof logging, as we'll see shortly, is a bit similar to how lazy clause generation works, in that it catalogues the steps taken by a solver in order to get to a particular solution. The difference being that the steps that are output have to be formally justified rather than simply asserted. But since we can see all the steps that the solver's taking, this could be a useful resource to mine for analysis, or even just provide some evidence that the answer really was produced by a real constraint solver. So this would be great if we can actually do it, and indeed anyone that's been involved in the SAT community in recent years will know that proof logging has already become established as the way to certify unsatisfiable problems. So this is done through the DRAP proof format. This is a Boolean clausal proof format, and it has a machine readable equivalent format that can then be verified, and that all works. Now, it would be great if we could just import SAT proof logging wholesale for CP, but unfortunately the more expressive formulations that we have pose a real challenge for Boolean clausal proof logging. So instead we look to proof log in a pseudo-Boolean format. So as a quick recap, pseudo-Boolean problems are essentially just integer linear, 0-1 integer linear programs. So here's the pseudo-Boolean constraint. It's a linear inequality over 0-1 variables. We use literals. These can take the values 0 or 1. We can negate them just as so, and everything here is integers. Now, pseudo-Boolean constraints can also be reified, and this is not entirely obvious when you first see them, so this can actually be done natively within the system. So if I ever write this, x implies some pseudo-Boolean constraint, this can really be just seen as syntactic sugar for putting a large enough coefficient in front of the negation of the reifying variable, so that if, in this case, x was false, then the rest of the constraint would just be turned off, so to speak. But if, on the other hand, x was true, then we would have to satisfy the constraint. So that's all that means. That's just a shorthand. Now, pseudo-Boolean constraints are naturally associated with the cutting planes proof system, which is 4 rules, very simple. So first of all, we can add 2 pseudo-Boolean constraints together to get a new one. We can multiply through by a constant. We can divide through by a constant with rounding, that's what the asterisk is. And we can always, no matter what we've got, introduce as an axiom that any literal is greater than or equal to 0, because of course it is, it can only take the values 0 or 1. So these rules together, you'll just have to believe me when I tell you they are sound and complete, so that when you derive a new pseudoboolean constraint from a formula based on these rules, you preserve satisfiability. And so you can construct a proof, because if you have a pseudoboolean problem, then you derive constraints until you eventually derive one that is obviously false. So for example, 0 is greater than or equal to 1. Then you have proved that the original problem is unsatisfiable. So that's great, and that forms the basis of the very PB proof system. And what makes the very PB proof system of particular interest to constraint programming is it's the cutting planes proof system augmented with some additional rules that make it easy to produce proofs and certify more expressive reasoning. Now, for the purpose of this talk in particular, the only thing that's going to be actually relevant here is the reverse unit propagation rule, which really is just a shorthand for cutting plane steps, but they're easy to output and can be verified via a simple procedure. So pseudoboolean unit propagation is lifted from the SAT terminology. It's just a generalization of unit propagation on clauses. From a CP context, you might think of it as repeatedly enforcing bounds consistency on the constraints until a contradiction or a fixed point is arrived at. So the reverse unit propagation rule says that we can introduce a new constraint via reverse unit propagation like this. So say we have this formula on this side and this constraint here, and we want to introduce that via reverse unit propagation. We can do that if the negation of that constraint unit propagates to contradiction. So we add the negation to the original formula, and then we repeatedly enforce bounds consistency, see what literals are assigned, apply that and simplify down, and you see that here we get a contradicting constraint. So it is indeed valid to introduce that via reverse unit propagation in this case. We then have some other rules in very PB. We have redundant space strengthening, which is useful for introducing fresh reified variables in the proof on the fly, like an extension rule, and dominant space strengthening, which is useful for optimization proofs and symmetry breaking, but I don't need to get into them for this talk today. So that is the basis of a proof system, and I should mention that although I'm going to focus in this talk on how to produce proofs of unsatisfiability, that's really just the core of then what we can extend to for proofs of optimality or proofs that we found all solutions. So we show how we can do unsatisfiability proofs, and then it's not too much of a stretch to say we can do optimality proofs and enumeration proofs as well. So the story last year was that it's possible to write a constraint solver in such a way that it prints out pseudoboolean constraints that justify the reasoning that it takes to produce proofs. Now, of course, I've been telling you about proofs in a pseudoboolean format, and now I'm saying that we can produce proofs for general constraint solvers, not for a constraint solver that's using pseudoboolean constraints, but for an actual expressive constraint solver that has all the global constraints that we know and love. So what the solver has to do is compile its problem down to a pseudoboolean problem first, that is then essentially on the side and used for producing the proofs, but crucially not for the solving process. And the good news is, because we understand very well how to compile constraint problems down to SATs, and pseudoboolean constraints are really just a superset of CNF, we can use well-known encodings for this. So for each variable, we can use a one-hot encoding or a binary log encoding. We want to encode the domains. And actually, I'm just going to assume that we have both at the moment, because as I said, using an extension rule, we can introduce fresh reified variables in the proof to get these on the fly if we want. And then we run the solver, and what we do, and I'm going to skate over the details of how this works just now, is that every time the solver backtracks, we output a reverse unit propagation statement that is the negation of the series of guesses that has led us to have to backtrack. So here we've guessed 0, 0, 0, and then we hit contradiction. So we would output this statement, which says that at least one of our guesses had to be wrong. And then we'll do the same as we continue down the solving tree. We backtrack, we output a RUP statement, and we backtrack, and so on and so forth. Until eventually what's going to happen is we'll have had to backtrack from the root node itself, in which case we'll have eliminated all the possible 0, 1 bit variables from our direct representation of the variable's domain, and that's going to allow us to RUP in a contradicting pseudoboolean statement and give us a complete proof. Now this would be great, and this would totally work if all a CP solver was doing was simple backtracking. But of course, the power of CP solving comes from the power of propagation and from global constraints. So to fit this into this proof logging framework, essentially what we have to do is whenever propagation is made, we have to somehow derive this pseudoboolean constraint here, which essentially says the series of guesses up to this point implies this propagation. Now, unlike the other statements, this might not necessarily be RUP. It depends on the encoding of the constraint that we're using and the power of that encoding, and also what we've derived prior to this statement to be introduced. So this is kind of where all the interesting research is that finding these constraints to derive in between to justify propagations to the solver. And so far, so in this paper last year, the story is that all of these global constraints that you can see here have propagators that you can write that work just as the standard propagators that we know for constraint programming, but can be producing pseudo-Boolean justifications for everything that they're doing to fit into this RUP on backtrack proof logging framework. And now what I'm going to tell you about in the second part of this talk is that we can now do this for two further global constraints that, because they are smart extensional constraints, can give us many other global constraints as well. Okay, so now I'll move on to the actual contributions of this year's paper. Now, by one technically correct and not very useful argument, we could already do proof logging for all constraints because we knew how to do the fundamental extensional constraint table, and every constraint can theoretically be expressed like this. But of course, we know that the size of tables can get prohibitively large, and by propagating everything as a table, we're not going to get a great solver for most applications. So in terms of a reasonable stepping stone from proof logging the fundamental CP constraints onto proof logging for the many specialized propagators that we have out there, we found that looking at these smart extensional constraints, or what we're calling smart extensional constraints, was a good place to go. So these are constraints that give us more or less explicit lists of permissible solutions, but incorporate shorthands to avoid some of the blow-up you would get with table. So specifically, we've worked out how to do proof logging for the smart table constraint and the regular language membership constraint, and we'll look at each of these in turn. So smart table is basically a table, but the tuple entries are allowed to be either simple binary or unary constraints or wildcards rather than just hard equalities. So you can see up here we've got B is allowed to be in the set 1, 2, in the first tuple, and in the second tuple we've got various different small binary constraints. But the same semantics still holds. Everything in that row has to be true, or everything in that row has to be true. So it's a bit like disjunctive normal form as well. And then in a similar-ish sort of vein, the regular language membership constraint basically allows the sequence of values, or only allows the sequence of values taken by a set of variables to be a member of a language recognized by a particular deterministic finite automata, which of course you can represent as a regular expression if you like. What these have in common is that they are able to give you decent propagation for a whole host of useful global constraints without having to implement a specialized propagation algorithm. The other thing is that the GAC propagators for both of the constraints are relatively non-trivial, so they both require their own constraint state and traverse graph representations in an efficient way to eliminate their unsupported values. So as well as giving us some kind of proof logging for lots of things, they're also a good litmus test for the VeriPB methodology in terms of its applicability to constraint programming. So let's get into some technical details, although I'll try and show this mostly just by worked example. So we'll start with smart tables. So for this we adopt a tuple selector encoding, and this makes heavy use of pseudoboolean reification, like I mentioned from earlier. So suppose we had something like I'm showing up here. This is the smart table example from earlier. The first thing that we've got to do is encode it as a PB formula so that we can produce proofs based on that encoding. So I'll use this to represent our proof space. And what we're going to do first of all is for each entry, we're going to have a PB variable that is set to true if and only if the subconstraint holds over the bit encodings on those variables. So here we're defining an E for entry for each of these simple constraints. So there's the B in 1, 2, the C equal to 3, and we would do them all for that tuple as well. So then once we've got these flags that represent whether or not one of these sub-constraints hold, then what we say is we'll have a selector variable that's set to true if and only if all of these flags hold for each tuple. And so we would do that, and then finally we say one of these selector tuples must be true. So that's basically just taking the smart table and producing the most obvious encoding we could think of to produce the same semantics in a pseudo-Boolean form. Then based on this encoding, we want to, as I said before, justify any propagations that are made during smart table. So if we stare at this table for a bit, we'll see that b equals 1 has no support in the table because a cannot be 1 and b is equal to a in the second tuple, and a is less than b in the first tuple, and b is in 1, 2. So that value has no support because it's not supported by any tuple. However, that doesn't actually unit propagate to contradiction under the encoding that we selected, which shouldn't be too surprising given the fact that we didn't select an encoding for propagation properties. So instead what we've got to do is we've got to figure out what lemmas, what sub-proof steps we can log so that that inference does follow by unit propagation in the pseudo-Boolean world. And we're going to use the way the smart table constraint actually works in order to do this. So from the propagator's point of view, the smart table propagator views each tuple as its own little sub-CSP, so like a tree or a constraint graph, and it requires for GAC that the constraint graph of each tuple is going to be acyclic. And then it does a two-pass filtering algorithm over the trees to collect what values are supported by each sub-CSP, and then infer overall what values are then not supported by any tuple and thus can be eliminated. So the trick is that we're going to log any of the sub-inferences made during the filtering process, but conditionally on these S tuple selectors. So for example, what the smart table propagator does when it's gathering what is supported by the first tuple is it filters based on these simple binary and unary constraint trees. So the first thing it would actually do is infer that if the first tuple is true, then b is not 1. And that's because of this subconstraint a is less than b. So what we would do in the proof log is then just have it output that inference conditionally, S1 implies b is not 1. And then we would do the same as we continue to filter. So from this subconstraint, we would infer that b is not 3, again conditionally, and then back to here, we would infer that a is 1, and from this one, we would infer that c is 3. And we would continue to do that for the second tuple as well, obviously filtering based on the second tuple selector. And then once we have all that, then when we do backtrack from our root nodes and we want the inference to be available, we can actually just rup in that b is not 1 based on inferences made by the smart table propagator, because we can log those two things, S1 is not 1 and S2 is not 1, therefore neither of them can hold, and because at least one of them had to hold, therefore we've reached a contradiction. So I realise I've just filled a slide with lots of PB constraints, and that may or may not make a lot of sense. But the essential point is just that this is easy to do, and in fact we can do this with only rup, and we use it following the methodology of the smart table propagator itself. So it's not like we're doing a whole load of extra work on top of the work that's already being done by the solver. So yes, there will be an overhead from this proof logging, but it's going to be some linear factor in the logging. So now on to regular, and it's a very similar story here. We're going to pick up a simple encoding, find that, surprise, surprise, it doesn't unit propagate unsupported values, but then observe that we can leverage the structure of the encoding and propagation algorithm to log enough things as we go along so that the stuff we want to add by rup really is rup in the end. So the underlying structure is a DFA rather than a table, but interestingly the propagation algorithm does have similar echoes in that it's also a two-pass filtering process over a graph. But anyway, so first we're going to encode the problem to PB once again. So we need to make use of auxiliary variables. So what we will define is some R variables, and these can be interpreted as saying the DFA is in state I after processing the first J symbols. So that's all that means, R00, R11. So then we say, well, at least one of these must be true. At each point, we must be in just a single state. And then we can encode our transitions like this. So R00 equals this, then implies the next R value, and so on and so on. So we encode all of our transitions using these R values to represent states. And then we also encode the non-transitions as well. So we say that any of the R combinations that have no path between them, we can't possibly have. And so we encode that as well. And then finally we say that we start in a start state and we end in an end state. So just very briefly, the regular propagator works by building a layered directed multigraph, where the ith layer corresponds to the states after j variables have been processed, and the edges are corresponding transitions between layers. The observation is that a variable value pair has support if and only if it is part of a path starting from the start state and ending in one of the final states. The propagation algorithm prunes edges from the graph so that only those that are part of a valid path remain, and it incrementally updates to maintain consistency whenever an edge is deleted. So to cut to the chase, in order to get our unsupported values to reverse unit propagate on the backtracking constraint, we need to log these edge deletions. So there isn't a single PB variable in our encoding this time representing an edge, but it's clear that the edge is implicitly two things: the R value that says state I is J, plus the xi equals V for whatever that variable value pair is. So to delete an edge, we have to say that these can't both hold at the same time. And the nice thing about the execution of the propagation algorithm is that it always moves in one direction and then the other. So we always know whether certain edges have already been deleted or not. So the long and short of it is, on the backward pass, we can just RUP our edge deletions, as the forward implications in the encoding propagate the inconsistent information on RUP and give us our contradiction. On the forward pass, however, we need to do a little bit more work, so we first have to exclude all the states that we don't reach, and then log that none of these states we can reach this particular node. This is the only point where we have to do strictly more work than the propagator does, but at worst you're only transversing the number of nodes in the graph, so we are still remaining within a linear factor. So that's the regular propagator. Obviously I've gone through all that extremely quickly, and for full details I'd encourage you to have a look at the paper. It's just a quick overview of what you need to do for proof logging these two constraints. I should say we have implemented and tested these in the Glasgow constraint solver and verified the proofs using VeryPB. Obviously this is all mostly prototype. I'm not confident that I've got the fastest or most efficient versions of these algorithms, but at least we are very confident we can say that they produce the right answer. So some concluding thoughts. The main point of all of this is that these two propagation algorithms, which seem involved on the surface, are easy to proof log in the VeryPB proof system, even without special engineering of the encoding. For the specific instances we implemented, in fact, we only needed the RUP rule, although this is mostly for convenience. You can log the same inferences via cutting planes with a bit of an additional engineering effort in the solver. So we're confident in saying that this is a useful step on the road towards certified CP. So next steps, these would include generalizations of these constraints that we've done. In particular, the graph representation of regular will be ringing strong bells for anyone who's worked with MDD propagators, and we're pretty sure that MDD type constraints can be proof logged in pretty much the same way. There's obviously many more important propagation algorithms to look at as well. I keep being told that I don't get to graduate until I've implemented all 400 of these from the global constraint catalog. But it's at least nice to know that we might be within some linear factor of them in a sense, because we can use representations as smart tables or regular expressions. And then finally, there's lots to do on the actual mechanics of proof logging. How can we make proofs more efficient to write and then verify? Can we take a PB proof log and trim it down before verifying, or mine it for analysis, as I mentioned earlier? There's lots of exciting things to look at going forward. So that's all I have to say. Up on the slide are some links to implementations and some other useful stuff. Thank you for listening.